Alright, I'm ZachQuintana and this is my NP hard reduction. In this video we're going to start by looking at the subset sum problem and showing that that's NP and giving a quick little example to kind of prove that. Definitely not a formal proof, but it does add up. And then the second part we will be showing a reduction of 3 sat, which is NP hard, to subset sum, and we'll kind of go through the process of that and see how we can map 3 sat to the input required for subset sum. So on the second slide here, I just have 2 paragraphs to kind of formalize the definition of subset sum and its solution. So we'll start with that. But essentially, the subset sum is we have an array of integer values, and we are trying to find some target, which is a target sum. And the solution is that there is some subset within this array that can be summed up to our target. So I have it here. The solution to the subset sum problem is a set of integers S1, which are derived from the indices of a given set S. So I'm just saying there's some subset of integers that comes from a main array. And it's this subset, when true, these values sum up to the given target T, and T is what's used more often than not with the subset sum. A lot of the examples I've seen. So given the overall set S, there will be a size n, so there will be some defined size for the array, and that size will actually help us prove the solution in polynomial time because we are given a size, and this will actually end up being big O of n. But again, it is in polynomial time, and so because the subset solution size will have a worst case scenario of the given size, and we do know that the polynomial input, this is polynomial input size by its definition, so it can be solved in polynomial time, therefore it does prove that it's NP. And I kind of touched that on the second the second paragraph here. So to verify this, so we have some certificate that we want to verify, and the solution of S1, which is our subset, we're essentially going to sum the values and then check against the target T. And each time we are adding these values, we're going to add, compare, add, compare, add, compare. If we were to iterate through the entire array. And this would be in hopes of finding a solution. And this will always be n minus 1, and it's kind of simple when you look at it. So the example I'm going to go with on the second page, that's kind of ugly, but so this is our S, right? So this would be n equals 7. So the size of our array is 7. But the solution will always be n minus 1 because we are comparing 2 values. So this would be 1, 2, 3, 4, 5, and 6. So n minus 1 is 6, and there you go. So this kind of shows that this gives us a hard constraint for us to verify that our solution will be in polynomial time, which goes to the definition of NP. So that kind of helps us prove very informally that subset sum is in the set of NP because its solution can be solved and verified in polynomial time. So I'm going to go through a quick example to kind of show this. So we're going to keep the same set, but I guess I'll draw the brace a little better, I guess. So I'm actually going to move this real quick. Okay, so that's our set. And our target, just from my baseball days, is 7. So we want to find some subset of integer values that are in this set that will eventually sum up to 7. So that's the question, and we can throw as many guesses as we want to try and get a yes answer out of this. We want a true answer because at the end, we'll get something. And is it true or is it false? So that's kind of like the only two paths that can come from this. So when we give our guesses, if we were to just straight up iterate through this, we will again get n minus 1 of total time. But I saved some time for this super difficult set. So, is there a subset S1 that is contained within S and adds to T? So sure, why not? Ooh, getting bad at writing these brackets. Okay, so we have a subset of two values. Okay, and we want to see if this is a valid solution. If the target will end up being equal to our sum here. So we're gonna add these two. Just do some basic math. So our sum is 7 there. We compare that to the target, and this could be in some programming algorithm. It could be you can do it dynamically depending on what type of NP problems you're looking at. But let's just assume somewhere in the code we're doing a comparison and we're checking against the target. We find that it's valid, so our sum is equal to 7. So then we can do yes. S1 is a subset of S. The sum equals to T. And that is, from my understanding, the most basic way to prove that subset sum is in the set of NP, because we have a size constraint. We know that it can be solved in polynomial time, and we just verified that, even though we knew the answer ahead of time, but we verified that it can be solved in polynomial time. So yeah, it took me a little bit to really understand that, because I do struggle with extremely large amounts of arbitrary aspects when it comes to stuff like this. So especially when we get to the reduction, kind of preparing to accept the arbitrariness of this problem was kind of difficult to get over, but I think I understand it pretty well now. We'll see here in a second, but yeah, so that's showing that it's in the set of NP. And you can kind of see on the last slide there, I ended up making a formal graph because my drawing's not so great. So what we're going to do here is now we're going to take an NP hard problem, because we know our subset sum is in the set of NP. And so we want to take an NP hard problem and show that we can reduce that to the subset sum. And we will do that here. So the 3-SAT is essentially, from what I understand, it's a Boolean. It equates to a Boolean expression that will have, it'll essentially have 3 literals and contained within brackets, and each bracket will essentially, it's called a clause. So we'll have these clauses, and we'll have a set of 3 literals. So it could be, and these are denoted by x sub 1, 2, and 3. I'm going to just use 3 overall. You can only have 3 in each clause, but I know there are instances where people add as many as you want. I'm just going to stick with x sub 1, 2, and 3. And these are all going to be ORed with each other. Okay, so that's a clause. That's clause 1 right there. So we'll do C1. Now, these are going to be ANDed with the consecutive clauses. So we'll just do it again. Let's flip these. So we'll bar these. Okay, and we'll call that C2. So these are our clauses, and this can continue on for however many you want. But essentially, we want this to evaluate to true. So eventually we want this to be true. So how does that happen? Well, each literal will map to an input for subset sum. So each one of these guys will map to a given input or a variable, depending on what you're reducing to. But another thing we need to keep in mind is we need each clause to be proven true individually. So each one needs to be true. We can't just have one or the other. They all need to be true for the entire Boolean expression to evaluate true. But not every literal in here needs to be true, which is nice. So do a little highlighting. So we can have x1. Oh, that's not good. Well, that's even worse. So I guess I'll use the pen. So we can have x1 is true, and then we could have these. All of these are false, right? Well, that expression is false because x sub 1 is true, and so the first clause is true, but then when we and it with the second clause, none of these are true. So then we would get false. But if we were to choose, and this is kind of hard without showing you the mapping to subset sum, but essentially if we had x1 as true and x2 bar as true, or if we chose that value in our guess, then that would evaluate to true. And so we would have the first clause is true and the second clause is true, and the expression evaluates to true. Very basic truth table type situation. But yeah, so we need the Boolean to be true or false. Each one of these x sub n, they can either be true or false, as well as their negation with the bar. So how do we take that and map that into the input of subset sum? So that's kind of like the whole problem with our reduction here. I guess we can kind of go over what the goal is. So the goal is we want to find some certificate that can be verified and checked that it's correct, and then we'll know by default, I guess, that subset sum is NP hard. And so that's kind of like our goal. We want to reduce 3sat to subset sum here. So I kind of have a setup. I'm trying to think if I should do it on this page or not. Okay, sorry. Had to do a little cut there. I started wandering off a little bit. So basically, I'm going to just kind of crop that out. So now we know kind of like a basic understanding of what we want to do, what the 3sat is, how do we satisfy that. But we want to reduce that to subset sum. So how do we do that? So let's say we have a Boolean expression, and we actually need it, so we will say. So let's do x sub 1. Let's negate these. And again, I'm just going to use 3. We're going to end up using 4 clauses. Most of the examples I've seen use 4 clauses, and I think I'd rather just stick with that and don't do anything too crazy to actually cause me to overthink this. But let's flip these actually. So after I'm done writing this, you might notice that this third clause is kind of cheating, but we are choosing these ourselves, so I will cheat to make sure this evaluates true. Oops, sorry, just moving that around. Oh, that's not right. Oops, sorry about that. We want those anded, so and all of these are going to be flipped. Oop, just made it. Okay, so might be hard to see since they're all white, but I think that's kind of clear. Clean this up. Okay, so this is our Boolean expression. So this is from our 3sat problem, which is NP hard, and we eventually want to take this and reduce it to some array, so some set. So we want to eventually turn this into, we want to take our subset. We want to take 3-sat and convert it into the input of subset sum. So a lot of examples do this with truth tables. Almost every single example I've seen has done kind of like a 4-quadrant type chart. That's the only one I've understood so far. The straight up truth tables, like hardcore, 0, like those I wasn't really getting, but down here below with the full chart definitely made more sense when doing the reduction into subset sum, at least. I'm sure there are other methods for other NP problems. But yeah, so we want to take our Boolean expression, take a guess from that, form it into our input, into our subset sum, and try to prove or verify that that is correct. Because if the subset sum ends up being true, we get a yes answer, then we prove that our 3-sat problem is true as well. We verify that. Not the other way around, so we can't just say 3-sat is verified, then by default subset sum is correct. But if we do verify that subset sum is correct, then our 3-sat problem is correct. So it's kind of like A to B, not B to A, which I do understand now. So, all right. So what I'm going to do is I will make a guess. And with the subset sum, so you can only have one of each, right? So now we're on the last page. I'm going to kind of zoom in a little bit. So you can only have one for each literal. You can only use it literal once. So that will give us down here, and this is how every single example does it, but it does make sense to me. So you can only use each of these once. Okay. So our target here is not going to be 7 because I don't want to do crazy math on the bottom, even though it's the difference of one number. So we will do a target of 4. So I've seen examples to do 3, 4, 5, 6. 4 is easy because you'll see the pattern, and I kind of like how the pattern turns out. So we have our target. Let's kind of separate this real quick. So on the left we have our literals, on the right we have our clauses. And so the left we can see we can only use each literal once, and on the right we have the target that we want to achieve, and we have all our literals up there. So how do we go about this? Well, first we need to choose our guess. So my guess is I want to choose, let's say this is just going to be the set of our guess. It doesn't really matter, but I want to choose x1 is true. I'll do x2 is true, and then let's say let's negate the last one. Okay, so x3 bar. So that's our guess, right? And so we're gonna eventually take this guess and create the input for subset sum. So how does this happen? Well, as you see down below, we have this essential, v1, v1 prime. So these are variables, and then we have what I couldn't understand for the longest time is that you can just generate scratch registers, or not registers, assembly, scratch variables, and you can use them however you want in order to help you get your target. I didn't think it could be as arbitrary as that, but almost every example, video, everything I've read basically says you can tailor this to your needs. You are making the guesses. You kind of own this choice. So we have on the left side we have 2 for each literal. We have x sub 1, 2, and 3 because each one has they're true or false, right? But instead of representing that as, also true or false with 1s or 0s, we need to represent the negated state. So v1 will map to our x sub 1 literal, and v prime 1 will be the negation of that. So we're basically going to populate this first quadrant on the top left, and give it the values of, populate the values so that later on, when we do make our guess, we will grab those values. So essentially we're saying that V1 maps to the literal x1 and its negation, to x1 bar. But that means the rest are 0 because we can only use it once, right? And this follows all the way down. So this entire graph is going to eventually have a diagonal of numbers going down to the right for the first and the fourth quadrant, which is interesting to me that always works out. So I just did that real quick, but essentially we map V2 to literal x sub 2, and same with 3 and 3. So I'm not going to fill in the left zeros because it does kind of make it confusing to me, I guess visually. But so we have our variables crafted now, right? But that's just for our literals. What about our clauses? Well, this is where we take the values of our mapping from the variables to the literals, and we see where they're true or false in our Boolean expression, right? So let's do those now. So variable 1, so x sub 1, is that true in the first clause? Yes, we can see that it's not negated. So that is, we can just say it's in clause 1, right? So then is it in 2? No, because that's x1 bar. So we're going to put a 0 for that. Is it in the third one? Yes. Right, so this kind of maps out very basically to that. So obviously x1 bar is in the fourth. So there we go. So that first row is done, right? So we're going to continue down this path, and we're just going to check which value is in each clause. So is 1 bar in the first one? No. It's in the second one. Not in the third, but it's in the fourth. Okay. Now is x sub 2 in the first one? No. It's in the second one. It's in the third. Not in the fourth, because that's x2 bar. Now x2 bar, that is in the first, not in the second, not in the third. And you can kind of see the pattern here, right? So each subsequent row will just be the oh, whoops, I kind of messed this one up. Will be the inverse of the previous row. So we have the first row that maps to x sub 1, then x1 bar, so the second row, that's just going to be the inverse. And I'm talking on the right side here, right? So we can kind of see that populate. So the third one, not in the first, and the second, and the third, and not in the fourth. And then we can just flip it, but we will confirm. So is x bar in the first? Yes. Not in the second, not in the third, it's in the fourth. Okay. So now our clauses are done, right? So we have all these values populated. Now, every example I was shown when you convert to subset sum is it uses a sum table like this, but how do you get to your target? So what is done is essentially you add downwards. So not sure who came up with this, but it's kind of a little genius way to do this. So if we were to right now just stop and try to add these up to our target, we can see that 1, 2, 3. That's not our target. So how do we get to 4? How does this happen, right? Well, and because, again, we're adding down and we want to get to 4, but we see that each one there's only 3, right? So how does it happen? And that's because we have 3 literals here. So how do we get to 4? Well, we have our scratch values, or scratch variables. So an interesting thing is that we are not using these for the literals. So every single video example I've seen basically proves that we do not need anything here. So, we'll kind of like forget about this section, right? So, because we're not using it, we don't need help with the literals, we need help with the clauses to get to our target. So, how do we go about choosing these values? Well, if you were to have, let's see, because you need one of these, right? So you're always going to need one of these. So this means at most we will have 3. We will have 3, I guess a count of 3, right? But what happens when we have less than 3? How do we get to 4? What if we have 2? So what if we choose x sub 1 and x sub 2 and x sub 3, right? So let's say we choose all of them, not the negated ones. Well, we would have 1, 0, and 0. Well, that's 1. So we need an offset, and we need a large number and a small number to, I guess, to offset whether we are at the max or less than the max. So right now, our clauses will have a max of 3. So what can we add down here to make sure we get to 4? Well, if we have a max of 3, we need 1, right? So how do we do that? Well, we're going to need at least 1. And what happens when we have 2? Well, we would need 2, right? So what we can do is just add, if we have the first one, we can have 1. The second one, we can have 2. As simple as that. Super arbitrary. We can change this to any numbers we want. Turns out almost every example I've seen that uses 4 as the target has 1 and 2. That is just the quickest way to get around this. If we had 5 literals, you can add more there, you can add less, you can have different, I guess, situations of that. But we also need, I guess I didn't explain this, because we need 2 for each clause. So people have done the math. 1 and 2 is the best situation here, but again, we can change that to anything. So we follow the same pattern, right? But why are we doing this? Well, it turns out that we will be converting Boolean values to decimal representations. Because remember, subset sum takes in a decimal, or integer if you're including negative. So it takes in an integer set of values, right? But with a 3-sat problem, we only have Boolean values, 1s and 0s. So how do we convert that to, a set that's not just full of 1s and 0s? Well, we essentially, what someone has figured out is you can convert. I wish the highlighters were working in this, but they're not very. Let's see. Oh yeah, they work here. So we added down. To get our decimal values, we just add to the right. But we're not adding, we are essentially taking that as a literal decimal value. So this will equal 1,000,010, right? So that is as easy as it gets, and it took me the longest time to understand that because I wasn't thinking of the mapping. So we are taking these Boolean values from 3-sat, all of this, right? Our guess and everything. So we're taking all that into decimals. So we're taking a true, and all of its representation down here, into some, some decimal value, right? So we will look at our guess. Just kind of remove that, and we will take our guess. So this is where you map your guess over here. Oops, that is not the highlighter. Well, doesn't work on, I guess, the blank background as far as I can see. But so we're going to take our guess and map that into our now finished truth table situation here. So I'm going to switch to green, remove this monstrosity. So we have x sub 1 here. So that's going to be our first row, right? Okay, let's do that. Right? So we used this one, so I'm just going to say guess here. We used x sub 1. So now we can't choose any other values there, right? So then our second guess was x sub 2. So that is right here. Okay. and that basically said we can't use that. So, and then we mark it off here. So then our third value we chose x3 bar. So that's going to be this row here, right? So essentially we are ignoring all of the other rows, right? You know what? We can make this easier, and we'll just mark them red because red is bad, right? So, oh, then I guess I should have used green for the other one. Oh well. So we see the yellow columns. Those are the values that we have so far. But as we can see on the right, we need to start counting our clauses, right? So we used up all of our literal choices. Now we need to see, do those map to our target? Well, let's start counting. So 1, we have 1 here, 0, 0, and 1. Well, that's 2. So how do we go from 2 to 4? Well, we have 2. So how do you choose which one you want? Well, you just go by the value that you gave it. So let's pull up yellow. So we needed the 2. So we're going to use that one, right? And remember, it's got to keep within the clause, I guess, the clause column. So and then we go to the next one. We have 1 and 0. Okay, that's not good. We need 3 more. Well, luckily we have 1 and 2. So for the second clause, we're going to use both of these. Okay. And then we'll kind of mark that off. Third clause, we have 1, 2, 0. Okay, we're going to need 2 again. So we're going to take this one and let's mark the others so we don't get confused, because when I do add these up, it does confuse me. So now we're on the fourth one. We have 0, 0, 1. We're going to need the last 2. Okay. So all we did here was grab rows that are equivalent to our guess, right? So we have our x sub 1 here, 2, oh, whoops, no, 2 there, and 3 all the way down here, or 3 bar. And then all of this is just to help us get to our target. Right, so now we can go, if we were to just verify this, so we had 1, that's not good, so we have 1, 2, 4, okay, that works. We have 1, 2, 4, works. 1, 2, 4, and 1, 2, 4, right? So let's clean up the right side here. So now that we have our guess mapped into our truth table, how do we go from this to the subset sum? Well, that's easy. We just take these values. So our set will equal 1, 0, 0, 1, 0, 1, 0, comma. I guess I'll write it up here. 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1. 2,000, 100, 200, 21, 2. So I guess a C-style array or Python dictionary, whatever you want to call it. So we have our set here. So we just took 3sat, a Boolean expression, took a guess from that, and reduced it, converted it to the input of our subset sum. Now we have to verify, that we can prove this, or that a guess is possible, that the solution can be found in polynomial time, because then that would prove that it's NP, at least NP. But essentially, this could be a stopping point because we did map the input to input. But I guess we will add it through and just verify that it's verify our solution is true or false, right? So I guess we can. Do I want to do long math? Let's see. Sure, why not? So, I'm going to pull up another page, and we're going to do some very long math. Actually, I won't. I'll just do it this way. So we have 1 million. I'm going to write it this way because it makes it easier when going down. So 1, 0, 0, 1, 0, 0, 0, 1, 2,000, 100, 220, 1, 2. Okay, let's add this all up. So we have 1, 2, 4. Okay, looks good so far. And I guess I didn't add this. So after you finish mapping it to the subset sum, your target is obviously an integer value. So we have our set of integers here, but our target turns out is the literal value. So 1, we just take all the numbers across. 3, 4. So this is our target. So we want that to map to our guess. If our guess is true and it's a yes answer, then that's, it's going to equal to the target we just wrote out. So 1, 2, 4. Okay, good so far. 1, 2, 4. Okay, 1, 2, 4. Looking good. And 1, 1, 1. Okay, easy enough. So, this was definitely not the first recording, but after some working, I was able to just kind of find the right guess to make this explanation easier. But yeah, we did see that this guess is correct. We can say yes. Our subset of, this entire thing over here. So I guess it would be our subset. This and then I guess I worded that wrong. So this over here is our subset, and then the entire this entire range of values is the set. All right. So our subset from there, yes, our subset. Let's see. Yeah, subset contain. We'll just rewrite this. Within set S, and we'll kind of, sorry, it's all over the place, but say sums up to the target T. Okay, so we just, with a very basic and very informal answer or example, showed that we can reduce 3 sat to subset sum. We took the Boolean expression up here, down here, converted it to our input, and found our subset. I'm trying to track my thinking here. Found a subset and verified it is the target. Right? We can get the target. So that, I hope, is enough to show my understanding of this. I tried to do the Super Mario Bros. Problem to subset sum, but they started using, I watched a few videos, and they kept calling them gadgets, but it kind of got into the whole ROP thing, where that's where I had it from. So kind of getting into that mindset was a lot more difficult than doing the 3 sat to subset sum. But it was rather interesting to see that, the Super Mario Bros., each, I guess, direction you go or each choice, you can't redo it. And so how do you map a final permanent decision to subset sum? And it was really interesting how they did it, but I didn't want to choose that because I still don't really understand that whole mapping, because they were essentially mapping a variable to each permanent decision, and yeah, it was very confusing for me, but it was really cool. I just decided to go with 3 sat because you kind of went through an example a little bit, and most of the examples I've seen were the 3 sat, or independent set. I've seen a bunch of other weird ones, but I went with 3 set because the Boolean expression was a lot easier to me because it's just ones and zeros. But yeah, so we mapped it to subset sum, and let's see, just going over my work here. Yeah, so we have the n-1 Boolean expression, found our subset. We mapped the literals to the truth table, added some scratch register. Okay, yeah, so this is the three set NP hard reduction to subset sum. Thanks for watching.